This session discusses mathematical modeling of mechanical systems. Mechanical systems can be classified into two types based on the type of motion: translational mechanical systems and rotational mechanical systems. Today's discussion is basically on translational mechanical systems. In translational mechanical systems, we can see that the motion of the system is along a straight line. In any physical modeling, there will be certain elements identified to represent certain specified properties of the system. Here we use mass, spring and damper, especially viscous damper, to represent the physical system. We know that mass is a distributed property, but we use it as a lumped parameter at certain points, and it is represented by small m or capital M. When this mass is subjected to a motion, it will experience an inertial force acting opposite to the direction of motion, and this value can be calculated using Newton's second law. It is given that the force is directly proportional to the rate of change of momentum. Hence we can write F is directly proportional to d by dt of m into v. This results in F is equal to m into a. In this figure, we can see that the positive direction is towards the right and the inertial force developed is towards the left. The next element is spring. In order to represent the elastic nature of the system, in the case of translational motion, we use a linear spring which obeys the Hooke's law. For a linear spring, the force developed in the spring is proportional to the resultant displacement for the spring. If the two ends of the spring moves through x1 and x2 units, then the resultant displacement will be x1 minus x2 if x1 is greater than x2. Hence, F is directly proportional to x1 minus x2, and we can write F is equal to a constant k into x1 minus x2, where k is called the spring constant. Next we have the damper. In the case of translational motion, in order to account the frictional losses of the system, we use a damper. It is also called a dashboard. To be more precise, we can say that it is viscous damper for the ease of modeling. According to the Newton's law of viscosity, in a viscous damper, the force developed is proportional to the velocity of the damper. Hence, we can write F is directly proportional to dx1 by dt minus dx2 by dt, since we need to consider the net velocity. Hence, F is equal to a constant b into dx1 by dt minus dx2 by dt if the two ends of the damper are moving through x1 and x2 units, assuming x1 greater than x2. In actual case, we can see that the behavior of frictional force is not that simple. It behaves in a very complicated manner. For example, when we consider the wall friction in the translational motion, it can even behave as a Coulomb damper. Coulomb friction, which is also known as dry friction, is not at all linear, but it is a non-linear function. Even it possesses a discontinuity around the zero velocity. So we cannot say that it is linearly proportional to velocity. For the ease of calculation, we use the viscous damping effect. Moreover, for a well-lubricated sliding surface, the viscous friction is more appropriate, and hence we use the element viscous damper. And while discussing the transfer function of electrical systems, we have seen that the order of the transfer function of an electrical system basically depends upon the number of independent charge storage elements. In the case of mechanical systems, the order of the system is proportional to the number of independent energy storage elements. The identified elements for energy storage are mass and spring. In the case of damper, we can see that it is an energy dissipator. Here we discuss some of the translational mechanical systems. Our aim is to derive the transfer function of these mechanical systems. To start with, we need to draw the free body diagram. A free body diagram depicts all the forces acting on the elements of the system. The basic idea is to separate all the elements into individual parts and see how the forces and reactive forces are acting on the system. In this case, we have a mass, a damper and a spring. First, we need to identify a positive direction of motion. Let us assume that the positive direction of motion is towards the right. When the mass is subjected to a motion, we can see that there will be an inertial force developed, and that is m into d square x by dt square acting opposite. There will be reactive forces due to this damper and the spring, which is acting on the system, and hence this will be in this direction. At all the points of separation, the net forces should get cancelled. That is, force and its reaction should get cancelled. So, here it is very clear that the force is pushing the spring towards the right, which means that the spring will be experiencing a tension due to the motion towards the right. So, here it is very evident that the spring is under tension. Maybe this can be treated as one point to check whether our directions are proper. Hence, this direction will be towards the left and this also will be towards the left. So, in short, we can see that since the entire system is moving towards the right, the force which is experienced by the wall will be towards the right. So, we can see that the directions that we have marked are proper. Now, in order to write the dynamic equation of the system, we consider the mass. Collect all the forces acting on the system and applying D'Alembert's principle, the net force acting on the system should be equal to 0. We have already taken the positive direction as the direction towards the right. So, f of t is positive, m into d square x by dt square is negative, b into dx by dt is negative, k into x is negative. Sum of all the forces acting will be equal to 0. This will be in the time domain. The differential equation will be in the time domain. Convert this into S domain and find the transfer function. The force is the cause and the displacement is the result. So, x of s divided by f of s can be easily calculated. It is 1 divided by m square plus bs plus k. Here we have a system wherein there are two masses, two dampers and spring. We can see that there are two displacements being marked in the system. To draw the free body diagram as mentioned before, first we need to identify a positive direction of motion. Since the direction of y1 and y2 are drawn downwards, we can consider this as the positive direction. Let us assume that y2 is greater than y1. Since y2 is greater than y1, we can see that both the elements k and b1 as well as b2 experiences a tension because the entire system is moving down. So, while drawing the free body diagram, once you mark the directions of the forces of the on the elements, we should check whether the spring and the dampers are experiencing either compression or tension. It is clear that the spring is experiencing a tension, the dampers are also experiencing tensions. Here f of t is acting downward, the displacement y2 of t is also towards the downward direction, hence the inertial force m2 into y2 double dot will be in the opposite direction. The reactions of the dampers will be also towards the top, hence as far as m2 is concerned, we can write this equation. Based on the marking of the directions of the forces and reactions, we can see that b1 into y1 dot minus y2 dot will be towards downward direction. Since the motion of mass m1 is marked downward, its inertial force will be towards the top. The spring experiences a tension and hence its reaction on the mass will be towards the top. Finally, we can verify the entire directions by checking what is the effective force on the wall. You can see that it is towards the downward direction. So is the case for the reaction by damper also. Here we have two masses, hence we need to consider two equations with respect to m1 and m2. The two equations are written and finally we can obtain the transfer function once we convert it into the S domain. So a point to be noted here is we need to first assume a positive direction for the displacement. Also assume which displacement is greater, and based on the effective motion we check whether the spring and the dampers are experiencing a tension or a compression. That idea can be used as a key point in marking the directions. Next, we consider the case when there is no mass. In such a case, what we can do is we can place a mass so that it is easy to write the differential equation with respect to that mass, assuming the mass m as 0. The free body diagram of the entire system is drawn here. It can be seen that towards the left end, we have a parallel combination of a spring and a damper. And the direction of motion is towards the right. As far as the spring is concerned, the effective displacement is y1 minus y2. We assume that y1 is greater than y2. Since y1 is greater than y2, we can see that the spring will be experiencing a compression. So is the case for the damper P1. And this is true with damper P2 also. Hence, the forces acting on the spring and the damper can be drawn as compressive forces. So the reaction will be towards the right as far as the mass m equal to 0 is concerned. The reactive forces on the mass m equal to 0 due to spring will be k into y1 minus y2 towards the right and b1 into y1 dot minus y2 dot towards the right due to the damper. Now let us consider the damper P2. The direction of the force acting on the damper will be like this. Based on this, we can mark the reactive forces on the mass as well as the wall. We can see that since the entire system is moving towards the right, the direction of the force acting on the wall will be towards the right. This shows that the directions marked are proper. Now we consider the mass m equal to 0 to write the differential equation. In this case, we have already taken the right side direction as the positive direction. So all the forces acting towards the right will be taken as positive and all the forces acting towards the left will be taken as negative. Hence, k into y1 minus y2 will be positive, b1 into y1 dot minus y2 dot will be positive, m into y2 double dot will be negative and b2 into y2 dot also will be negative. According to D'Alembert's principle, under dynamic equilibrium, the total forces acting on the system will be equal to 0. Hence, we can write this equation, which is in the time domain. Converting into the S domain, we get the transfer function like this. Next, we have a physical system wherein there are two masses, two springs and a damper, but the force is acting on the mass m1. The displacements are given as y1 and y2. It is assumed that y1 is greater than y2. Since y1 is greater than y2, we can see that the force acting on the spring K2 will be a compressive force, whereas the force acting on K1 and B1 will be tension. So keeping this in mind, we can first mark the compressions and tensions in the spring and springs and damper. Now coming to M1, the force F of T is acting down. The displacement is towards down and hence the inertial force will be towards the top. The direction of y1 and y2 towards downward direction is taken as positive. And since these two elements experience tension, the reaction will be towards the top. As far as the mass is concerned and as far as the wall is concerned, it will be towards the downward direction. So is the case for the reactive force acting on M1 due to the spring K2. It will be towards the top. As mentioned earlier, at every breaking point, the force and the reaction should get cancelled. As far as M2 is concerned, the reactive force will be towards the downward direction. Since Y2 is marked towards the downward direction, the inertial force will be towards the top. Now let us collect all the forces acting on M1 and M2. We can see that with respect to M1, since the positive direction is towards the downward direction, F of T is positive, M1 Y1 double dot is negative, B1 Y1 dot is negative, K1 Y1 is negative and K2 Y1 minus Y2 is negative. Then a force acting on mass M1 will be equal to 0 under dynamic equilibrium. So we have this equation. Now coming to M2, K2 into Y1 minus Y2 is positive, whereas M2 into Y2 double dot is negative. Here also the total force acting on M2 under dynamic equilibrium is 0. Using these two equations, which are in the time domain, and converting them into S domain, we can find the transfer function. The results are given in the lecture handouts under the session Transfer Function of Mechanical Systems. Thank you.